Next speaker is Pierre Py from Université Grenoble, and he will tell us about finiteness properties by complex geometry, Kapovich's work and its lineage.
Thank you very much. Thank you to the organizers for having me. So I want to tell you about how complex geometry allows to build groups with controlled finiteness properties, and that in the second half of the talk probably I will talk about joint work with Claudio Josa-Eisenrich. But first I want to tell you about an old paper by Michel Kapovich, which is really the beginning of the story, which started all of this. So first I will tell you things about finiteness properties and subgroups with weird finiteness properties built using holomorphic maps to Riemann surfaces. And the key thing we'll ask about these maps is that they have finitely many critical points. Okay, so we'll be considering closed complex manifolds and holomorphic map to closed Riemann surfaces with finitely many critical points. But then there are not so many examples of these things, so then I will explain to you how we can build more examples using, instead of holomorphic maps to Riemann surfaces, just holomorphic one forms. And here we'll ask that these forms has finitely many zeros. And at the end, if I have time, I will tell you a little bit about what some people call perfect circle value Morse function. Okay, so first, maps to Riemann surfaces. So the paper of Kapovich that I alluded to, it's a paper called, it's not a secret, you can find it on archive or on his webpage, it's just not published. It's called On Normal Subgroups. In the fundamental groups of complex surfaces. And it's from 98, more or less. I remember well. And it is about coherence of these fundamental groups. And so what is the main result? So, okay, if he considers a complex surface, X, closed and aspherical, and we'll also assume that it's a Kähler surface, so it has a Kähler metric, or if you want, it's just a smooth complex projective varieties, okay? X embeds holomorphically in some complex projective space. It's a bit more restrictive, but okay. And the theorem goes like this. Assume that you have a homomorphism from pi1 of x to a surface group. So if pi1x fits into a short exact sequence like this, you have a map to a surface group. So sigma G is a genus G surface, G is at least 2. You have a kernel. And if you assume that n is finitely presented, I will give a name to this homomorphism, let's call it phi. Then phi actually is induced by a holomorphic submersion from X to sigma G. Okay, so what do I mean here? I mean that there is a complex structure on sigma G for which there is such an F. F is a holomorphic map and it has no critical point. So this is what he proves. And there's another way to state it. First, I will assume that n is finitely generated, and I will just recall you some classical stuff from Keller geometry. So if n is finitely generated, it is known that any homomorphism like this with n finitely generated, it's always induced by some holomorphic map to a Riemann surface. Okay? But of course, you know nothing about the critical points of f. And this map F, it's essentially unique. And so another way to restate the theorem is to say that, okay, if n is finitely generated, I have a holomorphic map which induces the homomorphism to the surface group. And what Kapovich proves is that, okay, if n is finitely generated and the set of critical points of F is non-empty, so if there was a submersion inducing phi, it should be F, because this map F, it's unique, and here it's not a submersion, it has some critical point, so it tells us that n is not finitely presented. Okay. And so the fundamental group of X is not coherent. Okay, so this is Nisha's theorem. And how does the proof go? So I will just say a brief word now, and then maybe I will go back to it in a more general context later. So you look, you have this F. So this Riemann surface is just a quotient of the hyperbolic plane of the unit disk in C by some lattice. Let's call it gamma. And so you take the covering space of X, which fits into this diagram. So this is the covering space of X whose phi 1 is equal to n. And you decompose X as a union of larger and larger compact domains, which you just take, for instance, you take an increasing union of disk here, and you take the preimages. And if the n was finitely presented, the pi 1 of these compact domains, they would stabilize at some point. At some point in your sequence, they would become all isomorphic to the pi 1 of x hat. And then you get some contradiction. Okay, okay, so you write this. You write this as a union of disk. You write x hat as the union of the preimages of these disks. And if n is finitely presented, then pi 1 of x hat and pi 1 of the preimages of these domains, and this map here is proper, so these things are compact. They will be isomorphic at some point. But the thing is that if f has some critical point, then this, well, maybe I should call this f hat, it would be more clever. If f has some critical point, then f hat will have infinitely many critical points, okay? Because you have the surface group acting here on the critical points. And so at some point, these domains start having the same fundamental group as x hat, but when you increase them again, you see more critical points, and you will arrive at a contradiction if x is aspherical. Okay, So, okay, I will not say more about this now. But this is more or less the idea, to study these increasing domains and study the fundamental group. I will go back to this kind of argument later, but it's a complex analog of Westvina, Brady, and Brady's Morse theory. So, okay. So what did Misha deduce from this? He, using this, he gave the first examples of incoherent lattices in PU21, co-compact lattices. Okay. So it was known at the time that there are examples of quotient of the unit ball of C2 by co-compact lattice in PU21, which admits holomorphic map to Riemann surfaces, like this. So you get a short exact sequence like this. N is always finitely generated. Okay, if you have a holomorphic map to a compact Riemann surface, the kernel of the induced map at the level of pi1, it's generated by a smooth fiber of the map, so it's finitely generated, and it's known for ball quotients that these maps, they must have critical points. They cannot be submersion, and so the kernel cannot be finitely present. So this was the motivation of Kapovich. And just a side comment, because this is not so related to the rest of my talk, but there is a geometry and topology paper by Misha from 2013 where he has a conjecture that all lattices, any lattice in a semi-simple Lie group, which is not locally SL2R or SL2C, otherwise it's false, is incoherent. So using embeddings of F2 times F2, you can rule out many examples, and you can prove the conjecture for many examples. And in that paper, he proved it for certain lattices in PUN1 using while using these arguments, using all the theorems. So, okay, so yeah, this is using. Yeah, I will not say more about this conjecture, but at some point he proved this conjecture for certain arithmetic lattices in PUN1 using a totally geodesic submanifold and reducing to that theorem. Working a bit more. Okay, so now we'll go back to complex geometry. So what's next after the paper of Kapovich? There's a paper by Dimka, Papadino and Suciu, published in 2009, which deals with higher finiteness properties. So let me recall, maybe write a definition. So a group. Okay, we have already seen this appearing this morning, but I will recall the definition. So a group is of type Fk, or type F, if it has a Kg1 with finite K-skeleton. And for type F, you just ask for a finite Kg1, finitely many cells. And Dimka and Papadino and Suciu, they used similar ideas as in Kapovich's paper to build example of subgroups of direct product of surface groups, which are Fk not Fk plus 1, so this was not new, but the new thing is that these groups, they are fundamental groups of smooth projective varieties. Okay, so how did they do that? They start with an elliptic curve, just a complex torus of dimension 1. So C mod the lattice. And they consider several ramified covers of E. Finitely many. So you ask that the genus of sigma I is at least 2. And then they consider the direct product of these surfaces, take finitely many of them. And you just take the map, which is the sum of the pi. So you map x1 up to xr to pi1 of x1 plus pi2 of x2. And what is important, maybe I'll just use 1/2 of this more. What is important about this map, if you think about it, is that it has the critical set of this map is finite. Okay, it's just a product of the critical set of each pi I. So it's a product of finite sets, so it's finite. And they prove that the kernel of pi star, so the map induced on pi1, is, well, first it's isomorphic to the fundamental group of a generic fiber of pi. The generic fiber of pi, it's a complex manifold, and actually it's a smooth projective manifold, and it's of type of r minus 1 and r. Okay? But it's even not fp r of q. So r, one way to think of R here is just a complex dimension of the manifold you start with, because you start with a direct product of R Riemann surfaces. And the group you produce is Fr minus 1, not Fr. R is a complex dimension. Okay, so that's, yeah. Okay. So what's next? So after that, there was Claudio Josa-Eisenrich in his thesis. He did several. Okay, I said I was not going to write here, so we'll continue on the left. So he pushed further the work of Dimka, Papalim, and Sotiu. So first, he did several things. One thing he did was to distinguish between the groups obtained by this construction, so to prove that you can obtain many non-isomorphic groups like this. And another thing he did was to construct inside a direct product of surface group as the. So it's known that inside a direct product like this, you can find groups which are Fk, not Fk minus 1 for any k between 1, 2 and r minus 1, but what he did was to build example of subgroups like this, which are also fundamental group of smooth projective varieties. Okay. Subgroups which are I1 of smooth complex projective varieties. And so I will fix first an integer r between 2 and r minus 1. And these examples, they are F, not, sorry, it's K, they are Fk, not Fk plus 1. Okay, so when K is equal to R minus 1, it's the statement which appears in the theorem and here. And for lower values of K, he proved this using, iterating in some sense the construction of the dim K-Papalian switch. Okay. There's another paper on this topic by Brightson and Josa Eisenrich, where they build examples which are extension of dim K-Papalian switch examples. So they look like there's a normal subgroup, which is a direct product of surface group, and the quotient is one of these examples. But they do not embed into direct product of surface groups. So it gives example of pi1 of smooth projective varieties with exotic finiteness properties. They are not Fk, Fk, not Fk plus 1 for the right K, but they are not subgroups of direct product of surface group. Okay. Okay, now let me mention another result. I'll try to explain the proof. So in the work of dim K-Papalian and Suchu, you can really rely on the fact that you were starting with a direct product of surface group to prove the fact that the group is not of type Fr. And here is another result which applies to in a different context. So it's something I proved with Francisco Nicolas. So I will take any compact complex manifold here. So X is compact complex. And I will assume that I have a holomorphic map with finitely many critical points to some Riemann surface. So this is a holomorphic map. To a Riemann surface of positive genus. It could be 1 or it could be greater than 1. And I will assume that it has finitely many critical points, and that there are some critical points. It's not a submersion. So assume that the critical set of F is finite, non-empty. And then what we prove, and it's not difficult, is that if you look at the covering space of X corresponding to the kernel of the map induced at the level of pi1, so if this is the covering space corresponding to the kernel of F star, then if I call n the complex dimension of my manifold, but the Hn of this thing is infinite dimensional. And here I really don't need X to be a product of Riemann surfaces. Okay? So, some comments before I say a few words about the proof. So the same argument as in the work of Dimke, Papalian, Suchu, and Josa Eisenrich will prove that this space has the homotopy type of a CW complex with finite n-1 skeleton. probably finite n minus 1 skeleton. So this is the same argument as the work of Dimka, Papadimasuchu, and Yosa-Isenich. So it cannot have the homotopy type of a space with finite n skeleton. And so now if you add that X is aspherical, we get that the kernel of F star, it's pi 1 of the space X hat, so it cannot be Fn. Okay? So it's Fn minus 1, not Fn. It's actually not Fpn of Q. Okay, so let me give a sketch of the proof of this. So I will do exactly as in my sketch of the proof of Kapovich's result. So I have this space X hat. It maps to the universal cover of sigma, which is a disk. I will call F hat this map. And so F has finitely many critical points, so there are finitely many critical values here. So in the universal cover of sigma, I can picture all the lift of critical values. And there are infinitely many of them because the pi 1 of sigma is acting on this. So again, I will just write this disk as a union of smaller disk, and let's say that I will assume that when I pass from one disk to the other, I just add one critical value. Let's say that this is an increasing union of disks, and I will write X hat as an increasing union of the pre-images of these disks. And this is compact. And using some complex morph theory, you can show that this thing, I will call it xk hat. When you pass from xk hat to xk plus 1 hat, what happens at the level of homotopy types? The only thing that happens is that you glue finitely many n-dimensional cells. Okay, the real dimension is n. So xk plus 1 is obtained from xk. By gluing n sets up to homotopy. And okay, but if you know this, and using Meyer-Vietoris, you see immediately that the n minus the Betti number of degree n minus 1 of this xk will decrease. They're all finite because these things are compact. So if you look at the Betti number in degree n minus 1 of these things, this decreases. So they're all finite, this number, so this will become stationary eventually. And now if you write down what happens, well, after this decreases, you will get that you take k large enough so that this sequence is constant, and then you look at this number, and this will be increasing. Okay, what is the idea? It's just you have this domain xk hat, and you glue a cell of dimension n. So this sphere will become homologically trivial in the U space, but this sequence, if this sequence is constant, it means that it was already homologically trivial. So there was something like it was already a boundary. So here there was something. And so here what you see appearing is a new cycle of dimension n. Okay, so once this sequence is constant with k, this sequence b n of xk hat will be strictly increasing with k. And this is really close to what to the argument in Kapovich's paper. He did this with homotopy instead of homology, but it's the same kind of idea. And so then, since Hn of the space, it's just the limit of the Hn of the xk. It's, I mean, this has to be infinite dimensional. So this is more or less the proof. Okay, so what about examples to which you can apply this besides direct product of surfaces? So there are not so many examples. I will just mention two examples. I mean, finitely many examples. There is one example which is a quotient of the unit ball of C2 by a co-compact lattice. It's called the Cartwright-Steger surface. And it's an example where you have a map to an elliptic curve with finitely many critical points. And there are some critical points. So it was discovered by these people when they were trying to classify fake CP2s. So it's a complex surface with Euler characteristic 3 and first Betti number equal to 2. And so you can use this example, for instance, and to do the same thing as in Dimka, Pavalim, and Sushi's example. You just take several copies of X, and you look at the map which take X1 up to X1 to f of x1 plus f of x2 plus f of x1. And this map has finitely many critical points, and the kernel of f star is contained in the direct product of R copies of this lattice in PU1. Okay, so gamma is a lattice in PU1. And this will be f to r minus 1. To r minus 1, not f to r.
So Pierre, just to make sure I understand, I think it looks like a B2 in the top, but that's a two-dimensional complex.
Yeah. So it's a unit ball in C2. It's a unit ball in C2, and
unit ball in C2. Okay.
So its group of holomorphic automorphism is PU1, and so gamma is a torsion free compact lattice in here. Yeah. Okay, so this is one example, and this group is also the pi1 of the smooth projective varieties, and maybe I should mention another example which appears in a joint paper with Claudio, which is a subgroup which is a fiber product, but which is not a normal subgroup. So there is another example of a gamma like this. So there is an X of the form B, again B2 mod gamma lattice in PH1, with a holomorphic map to a high genus, let's call it F, to a high genus Riemann surface. And one thing we proved with Claudio is that if you take, so you have this X with a map to sigma G, you take a ramified cover of the sigma G, and you take this ramified cover so that the critical values of these two maps are disjoint. So you assume this, you can always do this. And then, well, this does not follow from the previous theorem, but you can show that if you take the fiber product at the level of pi 1, this is F2, not F3. It's the same kind of idea. Here it does not, since it's a fiber product construction, it does not follow from what I stated before, but okay, it gives you an example of something. This P is also the fundamental group of smooth projective varieties, and it's F2, not F3, and it sits in this direct product, but it's not normal. It's a fiber product. Okay. So all these constructions, I give you example of groups with controlled finiteness properties. They're always Fn minus 1, not Fn, if you started with a complex n-dimensional manifold, and they're always pi1 of a Keller manifold or even a smooth projective manifold. Now there are not so many examples besides direct product of Riemann surfaces or quotient of the unit ball of C2 because there are not so many examples of maps to Riemann surfaces with finitely many critical points. For instance, we don't know the following. So if n is at least 3, we don't know if there are quotients of the unit ball of Cn by a co-compact lattice torsion tree, admitting a holomorphic map with finitely many critical points to a Riemann surface. So it's known that there are, I mean, if there's a map like this, it must have some critical points. It cannot be a submersion. But we don't know this. And actually, this question maybe is a bit ridiculous because even if you remove finitely many critical points, the question is open in dimension at least 4. So in dimension 3, there are examples of maps like this with an infinite critical set. And if you go to dimension 4 and higher, we don't even know if there are maps like this, without even asking about finitely many critical points. Okay, so now let's go to holomorphic forms. I'm quite late, but okay. Holomorphic 1 forms with finitely many zeros. And by considering these objects, we'll see that we can build more examples of subgroups with controlled finiteness properties. The difference is that the subgroup will construct, they are not pi1 of a Keller manifold or smooth projective manifolds, but still they are very interesting. Okay, so first forget about complex geometry for 2 seconds. So consider X, which is a real manifold of dimension 2n. Closed as spherical. And suppose that on this manifold you have, well, depending on your taste, you can think in terms of one form or maps to the circle. So if you have a map, let's say to S1, which locally looks like the Morse function, so it has finitely many critical points. And we'll ask even more. We'll ask that all its critical points are of index half of the real dimension. Okay, so in some coordinates locally near a critical point, it's like it takes x1, x2, up to x2n to the sum of the squares of the first n coordinates minus the sum of the last n coordinate. Okay? So the index is n. And if you have a map like this, using a Bezdina-Bareilly type argument, or argument as I explained before, it's easy to see that the kernel of f star is fn minus 1. Okay, because you take the cyclic cover of X corresponding to this map, and you look at this covering space, and you want to understand the relation between the topology of the covering space and the topology of a smooth fiber. And when you pass critical points, the only thing that changes is that you glue n cells. So you kill n minus 1 dimensional spheres. But so it's nothing happens on smaller, homotopy group of smaller decays. So if you think a little bit about it, you can prove this. Okay. And it's a classical fact that if the Euler characteristic of X is non-zero, you can show that the kernel is actually not Fn. Okay, so everything I'm going to talk about now is based on joint work with Claudio Josa-Eisenrich. So now what I want to explain is how you build manifolds like this, admitting plenty of such maps. Okay, what is a natural way to build maps like this? Okay, so I will try to explain this in 4 steps. Okay, there'll be 4 steps. So first, okay, I will look at H1 of X. So I think of this as a Doram cohomology group. So this is some space of closed form modulo exact forms. And here I will consider the set ON, which are just the classes represented by Morse forms. So a closed one form, I call it Morse. If locally near 0, it's a differential of a Morse function. Okay. When you have no 0, locally it's a differential of a submersion. And when you have a 0, I want it to be the differential of a Morse function. And here I will ask that all the indices of the zeros are n. So a class is in O sub n if I can represent it by a closed one form, such that near any zero of my form, the form is like the differential of something like this locally. And it's a fact, or it's an exercise that you want that this thing is open. So the only thing we care about is to build manifolds where the set is non-empty or it's big. Because if I have a class here, if it's non-empty, then there are some rational classes in it. And if I have a rational class, I can multiply it to get an integral class. And if I have an integral class, it comes from a map to the circle. Okay, I can integrate the form and divide by the group generated by periods. It's cyclic, so I get a map to the circle. So it contains rational class if it's not empty. Okay, so this was the first step. So now, how do you build a? Okay. Example where the set is non-empty. So here we'll have to start assuming that X is a complex manifold. So assume that X is closed. Well, it's always closed. Well, let's assume that it's Keller. So it's a complex manifold and it has a Keller metric. And And I will also assume, well, in this case, first, we know that if you take alpha, which is a holomorphic one form, so a form which takes complex values, this is always closed. And if I take its real part, this map gives an isomorphism between the real value like h1 of x and the space of holomorphic one form. Okay, so this is an isomorphism. This is the content of Hodge theory. Another claim is that if alpha has finitely many zeros, then the real part of alpha lies in this open set ON that I mentioned before. Okay, so this is not very difficult to see. I will just explain it in one special case. If I assume that really alpha is morphs in the complex sense, so suppose that alpha near 0, it's really the differential of a complex morph function. So it's like the differential of z1 squared plus z2 squared up to the n squared. I mean, the general case is a bit more involved, but I assume that near each 0 of alpha have complex coordinates like this, so that alpha locally is given by the differential of this. And then in this case, there is essentially nothing to prove because the real part of alpha is just, if I write zj as xj plus I yj, then the real part of alpha is just d of the sum of the xi minus d of the sum of the y. So locally what I see is the differential of a morph function with a critical point of index n. And okay, in general, if I have a form with finitely many zeros, locally near 0, it doesn't look like this, but you can morphify it, let's say, you can modify so that it looks like this. So, okay, so this is the main claim in step 2. Okay, so now what is the third step? Well, the third step is how do you build manifolds having many holomorphic one forms like this with finitely many zeros. How do you do this? So, okay, if X is a Keller manifold, you can build a complex torus. I will call it A of X, sometimes called the Albanese torus, and it's what is its dimension? It's 1/2 of the first Betti number of X. And there is a map, holomorphic map, let's call it A sub X, from X to the torus, which induces an isomorphism on H1. On H1 with real or rational coefficients. Okay, and now the claim is that if AX is an immersion, or what you really need is what is called a finite map. What does this mean? Finite means that the preimage of any point in the target by A sub X is finite. So this is true for an immersion. So here immersion is an immersion in the sense of differential geometry. So if this is an immersion, what's going on? Well, then there are plenty of holomorphic one forms with finitely many zeros on X. Then a set of holomorphic one forms with finitely many zeros is dense in the space of all holomorphic one forms. And because of the previous step, if I look at the real part of this form, it will be a dense set in H1 of XR, and it implies that this set that I call O sub n is dense. Okay, so maybe I'll skip the proof of this. So this is a complex geometry argument. I will skip it. And then we have to build examples of manifolds with which are Keller and which have a map like this, which is an immersion or finite map. And for this, there is a very nice theorem of Philippe Essidieu. It's hidden somewhere in some unpublished preprint, but there is a proof also in a paper of Claudio and myself, and the proof is really not difficult, so you should not be scared. This is a beautiful theorem, but it's not it's understandable. Really, no, don't be scared because there's some complex geometry or whatever. So you take a lattice in P1, let's say that it's co-compact torsion free. Okay, so this map here, I will give it a name. It will be useful, so it's called the Albanese map. And what is the theorem here? The theorem is that so assume that, okay, you have to assume that gamma is arithmetic, and that it has positive first Bettina. And there are examples of lattices like this. And then the theorem says that after taking a finite index subgroup, you can take gamma naught in gamma of finite index, such that for the manifold, which is just the quotient of the unit ball of Cn by gamma naught, the Albanese map is an immersion. So in particular, you can recap and you can go backward and you can apply everything I said before to these examples. And so this gamma naught, it's a hyperbolic group, and it has many homomorphism to Z. With kernel of type f n minus 1, not f n. Okay, because it has many cohomology classes that you can represent by Morse forms like this, and which are integral. Okay, so there are 5 minutes left. Okay, so what do I want to do now? I want to mention another construction. There are more hyperbolic groups which admit maps like this. So there is something called the Stover-Toledo manifold. What are these things? these are ramified covers of wall quotient as above. So there are ramified covers of this quotient of the ball by arithmetic lattices with positive V1. There are Kähler manifolds, which they admit Kähler metrics of negative curvature, so the pi1 is hyperbolic. But the pi1 is not, it's not a lattice in a simple D group. So there are other examples of hyperbolic groups. And you can build this manifold starting from something like this, starting from an X where you already know that the Albanese map is an immersion. So this means that you can also build Stover-Toledo manifolds to which you can apply everything I've said before. So there are examples of such manifolds, such Stover-Toledo manifolds with maps whose pi1 has morphism to Z, with kernel of type Fn-1 out of. So it gives even more hyperbolic groups with a subgroup of type Fn-1 not Fn for any given n in advance. N again is the complex dimension. Okay, so I think I will forget about the third part of my talk. I just want to mention one more thing before finishing. So here we have we have built subgroups with exotic finiteness properties which are kernels of map to Z. But here is something else we proved with Claudio. So there are examples of X. So complex dimension of X is always n, which are either all quotients or Stover-Toledo manifolds. With surjections of pi1 of X onto Z2 with kernel of type Fn-1. I don't know about higher rank abelian groups, but for Z2 we could prove this. And I will just say one word about the proof. So for homomorphism to Z, we could argue with a basic Morse theory. And to prove this, we have to use things about BNSR invariant, Bierry-Neumann-Streubel-Renz invariance. So there's something called sigma n minus 1 of pi1 of X. This is the n minus 1 BNSR invariant. So for n is equal to 2, this is just the sigma 1 that probably most people know. And the key observation to prove this is that if you have a holomorphic 1 form with finitely many zeros, so alpha is the form as before, well, I can multiply it by a complex number of modulus 1, and it still has finitely many zeros, and I can take the real part of this. And so I get by varying theta, I get a circle in this set. We can prove that the class of the real part of this form lies here, and I get a circle. And now if I perturb the circle so that it's rationally defined, it will basically give me what is written here in the theorem if you know about BNSR invariance. Okay, so I should stop here. I have 7 seconds left. So I will stop.
Are there any questions for Pierre?
Yes?
These Stover-Toledo manifolds, is it known if they're residually finite, or are they that?
It's not known.
But it sounded like you were saying this Isidore theorem does apply to them. Is that right?
No, it doesn't apply to them, but
Okay.
the thing is that to do this construction of Stover-Toledo, you can kind of choose which ball quotient you start with.
Okay. So you maybe.
And so let's say that you have a ball quotient, and you do the Stover-Toledo manifold, which is a ramified cover. This Albanese map, I mean, here I have this Albanese map. And this is finite, so the composition of the two will be finite.
I see.
So this is enough for...
I see. Right, okay.
Do you know if for the Stover-Toledo, is like the first Betti number increasing?
The first Betti number, does it increase?
Yeah.
No, I don't know.
But does it? So that
I mean,
that map it also says that the map to the Albanese of the Stover-Toledo is finite as well.
Yes. So it could increase, it could be equal, I don't know.
One final question before break? If not, let's thank Pierre again.